in that type of problem. Now, as I understand, as Chitabro was telling me that we have a mixed crowd here. So many of you may have graduated in physics. So the statistical physics, the elementary statistical physics that I will talk about will be very elementary for you. You have to bear with me, or you can feel sleepy, you can blame it on the food what you have right now, right? So I will start with what is collective behavior and how we try to understand it. 1 hour or 1 hour? Okay, fine. So as I said, I will not go in details of each and every derivations or something, but I will go through the key things that we need to understand the concepts, right? And the limitations also. So every one of you know the, what you are well aware about collective behaviors, right? So at every scale, starting from molecule to in the organism scale, in the ecosystem scale also, you see collective behavior. Obviously, common thing in human is when a mob go and lynch somebody, that's a collective behavior definitely. I may be very polite and talking very nicely to you right now, but when I'm in a mob, you cannot expect that what type of a horrendous person I could turn out to be. And that's the collective emergent behavior that comes out. Many of you may have danced in mob flash things, that's a collective behavior. And you must have, as I gather from your backgrounds, that you must have seen videos on flocking of fishes, birds, and all these things. I will not go on all these things. Just before coming here, I was wondering how to start, so I just looked into the dictionary. Nobody looked into nowadays in printed dictionary. Most probably none of us has that anymore. So the online dictionary tells me that collective behavior is a mass behavior of a group of animals, a very lame definition. It doesn't match with our expectations actually. So if you dig into further, Britannica gives some confusing thing. It's a long article, but focused primarily on psychology. But there you get some keyword. Yes, the collective behaviors is spontaneous. As I gave the example of mob lynching another person, I may be just enjoying the Golgappa somewhere in the street. All of a sudden, spontaneously, I become a violent person, right? So there's spontaneous emergence of this property. And obviously, there is no authority. But you have to remember that, because I will come back to our problem also and while discussing. No authority does not mean there is no authoritative link in it, right? When we will talk about collective behavior, most of the talk and paper will always talk about local interaction. There is nothing governing, there is nobody controlling, but that does not mean there is no global cue. There can be global cue, and that can shape collective behavior. In my presentation, I will show that also in one case, right? A particular case. But the primary thing is actually the main driving force is not the authority. It is as a whole the crowd, the ensemble is developing the thing, fine? So now, based on this type of keyword, we will evolve. We do not have actually a very good definition, right, that you can teach in an undergraduate class for collective behavior. But let us look into a few examples. And I'm sure those examples of flocking of bird is a cliche, so I will not go there. Let us focus primarily on example from cells, right, individual cells. Planar cell polarity that I will talk of is a higher animal, right, eukaryotes. But even although most of the time we think bacteria as a lonely individual enjoying their life freely, right? That's not true. They have a collective social life. And in this case, a very well-known thing, this bacteria can be dangerous in terms of medical issues. But here they have flagella, and they can different types of motility. For example, they can swim, they can slide. And what I am showing you here from this paper is we call swarming behavior. So they spotted the bacteria here and somewhere in the middle, and the agar is not really very hard. It is a bit soft agar, so that now the bacteria can move. Now you can imagine if there is no coordination, I will see as usual it will be a circle which is spreading out, isn't it? But here you don't see that. You see particular pattern, right? The pattern emerge because of this swarming behavior, where these some of the bacteria here may have started moving on their direction, and then when they move, they actually release something which are called surfactant, which helps other bacteria to move over the surface, right? Just like the ant, when they walk, they keep on giving the pheromone, the other ants follow. The same thing is happening here. And at the same time, there is a collective phenomena called quorum sensing, right? Each bacteria can actually sense how many other bacteria roughly is there. Based upon that, they change the gene expressions, right? And the release of surfactant. And as a whole, you have this swarming behavior. Fine? Now, let me go to another example. This is a very old 71 paper, and Maitreyi was saying something similar to this. that how thermodynamics, actually equilibrium thermodynamics can be used to understand tissue pattern formation. These type of experiments actually led to those ideas, and eventually the idea of cellular pots model, which is very useful and powerful in these type of questions. So what you have here is that chick embryos, they have collected two types of cell. They may homogenize it, put in a liquid culture, and then in a suspended culture, right? And then they allow it to evolve. So what you see eventually with time, they segregate, two types of cells segregate, right? So in fact, this type of experiment, as I said, led to the idea of cellular pots model, where you consider a very simple thing. The simple logic is there is an adhesion energy, right, which could be homophilic, heterophilic, fine? So these black cells, dark pigmented retinal cells, they want to stick to each other. So the energy cost is less. Whereas this white one, the neutral retinal cell, they also have a homophilic thing, right? So now if you allow this whole system, remember the important word, the whole system, not individual cell, the whole system as a whole to reach a thermodynamic equilibrium, then the system should reach a minimum free energy state, and this is the minimum free energy state, fine? Now this whole thing is in a way is a collective behavior, because the homophilic interactions are there, that is reducing the free energy, and that's why the segregation is happening, right? This is a classical cell sorting experiment. Now let us move to something else. Cardiomyocytes, the bits, and at least when I go to give talks to school children, one of my favorite video from YouTube is that where the isolated cardiomyocytes are beating, right? That is available. Very interesting to show to children, right? So, actually, as we know, just like fireflies synchronize their emission of light, right? Flashing. These cardiomyocytes, when they make a tissue layer, they have to synchronize, entrain their frequency of beating, right? So in this experiment, it's a very interesting experiment. What they did, they take individual cardiomyocyte in suspension, and you have this, laser engrave, what we can say, they have, using laser, they make wells. In each well, you put one cell at a time, right? And you allow in some cases to make the connection between two wells, so that two cells can make connection. In this particular one, only one cell can be there. There cannot be any connectivity between two cells. Here, two cells is allowed to connect. Here, an array of 9 cells, each other interacting with each other because there is a channel between them. So when you see them, these one cell units, you will see each of them is beating, but this beating thing is quite irregular. As you put other members, other cells, they try to entrain, right? And the CV, the fluctuation between beating interval, start dropping. That means a synchronization is happening. So this is another classic example of collective behavior. Stogast made the what we call firefly synchronization quite a common topic of discussion, but this is equivalent to that one, right? This is, you can actually model it using a simple two oscillators connected with each other and then getting entrained, right? So these are all examples of collective behavior. Based upon these, let us make a working definitions of what we mean for this, at least for this lecture and the consecutive one. What do I mean by collective behavior? Collective behavior is coming because of I have ensemble made up of entities, agent, cell, human being, whatever you call of, and they can be homogeneous, heterogeneous. Although most of the time we talk of homogeneous, one type of thing, but you can always imagine multiple type of them, and they have local interactions with or without global interaction Q, we have to remember, and that generates some novel properties, right? Right, order to disorder, disorder order transition, formation of pattern, collective movement, or synchronized dynamics that I am showing, and this part is sometimes we forget. See, when we create models for inanimate objects where collective interaction, local interactions are there, right? For example, a magnet I will show, right? The classic icing model. See, the interaction does not change the property of that particle, right? But remember, when you talk of a cell or an individual organism, these local interaction and the emerging property that are coming up will change the behavior. If you consider a cell, it's a gene expression pattern itself, right? So it is like from lower level, an emerging higher property comes, and that higher property again work on the lower level to change. Both way, right? This part is actually not quite well understood, because it's very difficult to wrap around our head to this idea that something is coming up and then that control you. One classic example that I give in class is that, think about this, the people who are in parliament in power, they have come up because of the local level political activities. Now what they do in the parliament and make the policies again come and affect your life every day. So it is a two-way connections. right? Most of the time when we make the model, we miss this one. It's difficult to actually achieve. Now, if this is what is collective behavior, then if you have read lot about collective behavior here and there and listens talk, then you must be heard about that. When people talk about collective behavior, another term come with it is called self-organization, right? So what is self-organization? If you ask this question, honestly, me or anybody else really doesn't have an answer, right? Like, for example, what is vulgar? We do not have a definition, exact definition for that, but we understand what is vulgar, right? The same thing is what is self-organization is. We do not have a clear definition that 1, 2, 3 I can write down or mathematically represent, and I can say, bang, this is self-organization, this system is self-organizing, this system is not self-organizing. No, we do not have such definition. So, but we have certain ideas. The idea is that, and if you have not read this book, I will insist that please get the copy of that and read it. It's an excellent book to read, and at the same time develop some ideas and get ideas of the debates in this in case of self-organization. So self-organization is where you have the pattern form. Remember, the pattern can be temporal and spatial both, right, or either all of them. And at the global level, because of the interaction at the lower level, and one important thing is that they are using on the local information. There is no global pattern which can lead it, right? Against the example in the Britannica thing, they said there is no authority, global authority. So this is how self-organization is defined in this book, and I found this one is comprehensive one to actually capture all these ideas. Now, when you say this, don't say this in front of a chemist, particularly structural biologist or somebody who has worked long on chemistry. They will immediately say, why are you creating a new term? You're just a mouthful thing. This is self-assembly. You take the virus particles, right? Virus envelope is made up of multiple proteins, right? Heteromeric, right? So you purify them separately and then mix them in PBS, leave them in room temperature. They will assemble and make a viral particle. That's how we make empty viral particles in lab regularly, right? So that's also local interaction, right? We don't call them self-organization. For ages, we call them self-assembly, right? So what's the difference between self-assembly and self-assembly and self-organization? So this debate is there actually to say what we will call as self-organization, what I should call as self-assembly, because both of them, a global pattern is emerging, global order is coming from disorder, because when you take this protein, they are disorder, right? They are individual unit roaming in the liquid, right, in the solution. And when they come together because of local interaction, they make a structure, ordered structure. So should I call it self-organization? The sort of consensus right now is that you do not say that self-organization, because you can explain that in terms of equilibrium thermodynamic concept. Because in that case, the local interaction between these two molecules eventually led to a structure who has a minimum free energy, right? So that's why it has stabilized. Fine. Those people who say that, they insist that you should consider only those systems which are away from equilibrium and showing this type of collective behavior as a self-organizing system, right? Okay, so far so good. If now I move into another related question, because these will come up, because these are overlapping terms that we discuss when we talk of collective behavior and the physics of that. See, every time you will read any collective behavior thing or talk to people, they will say that there is something, a threshold behavior, a critical behavior. And nobody can understand that like any teacher who can teaching a undergraduate students of suppose 100 students in a lab. Suppose 100 students in a lab, whatever you try, some of them will talk to their neighbor, right? You do not pay attention to them, because if you pay attention, they will talk more and harass you more, right? So you allow 1 or 2 people to talk, do not do the experiment, they are doing something. But then, as 2 people, the students are talking, third one joins it, till you intolerate it. But then, after some time, a threshold is crossed when almost the whole class of 80 students are talking to each other. Then you cannot take the class. This is a common phenomenon, right? So there is a threshold. How many students you will allow to disturb, right? If you cross that threshold, the class goes out of your control, because as a whole, everybody is talking, there is a huge noise. The same thing if you have seen any flash mob activity dance, right? initially those people who have planned the whole thing has come, they're the seed, right? 3-4 people, they start dancing. Then maybe somehow you joined, but that doesn't mean that as a whole the 20 people are dancing. Then as a critical mass emerge, suppose 14 or 15, then all of a sudden a large crowd joins in, right? So this is a threshold behavior is there. So this type of threshold behavior are very common and to think is very simple to think of, and that's why people will say that this collective behavior and self-organization are essentially some sort of phase transition. Because if I don't go in details about symmetry and other issues of phase transition is something where I am moving from one qualitative state to another qualitative state by varying one or more parameter very smoothly, and there is a point, critical point, beyond which my property changes drastically, abruptly, right? And from your undergraduate levels physics, we can know, as I have shown here, there are, this control parameter is controlling the phase transition. I can have two types of phase transition. This is a continuous one, continuous phase transition or second order phase transition, whereas this has a discrete jump, right? So both are anyway critical phenomena. Now, why I have shown this one, this is also a critical phenomena, but usually we do not call them phase transition. This is a bifurcation diagram, and I believe there are multiple lectures on bifurcation, where bifurcation has been touched upon here, right? So this is a typical what we call supercritical pitchfork bifurcation, right? And in this case, you have a critical point. Before this critical point, when the control parameter is lower than this critical point, you have only one stable steady state possible. The system will always be there. Whereas after that, there are three steady states appear. Two are stable, the dark lines, and the dotted line is unstable. System can go either on this, depending upon the noise here. Now, this is also a bifurcation point. This is also a critical point. And obviously, as I cross this, either on this way or from this direction, it doesn't matter, my quality of the system changes. So this is also a critical phenomena, and I will touch upon, actually I can show this fellow and this fellow are actually equivalent. Actually what we study in, see, remember this is not coming from any thermodynamic consideration. This is an arbitrary dynamical system, whereas this comes from thermodynamic consideration, but I can actually show these two are actually equivalent. Okay, so this is very easy to perceive that there possibly the collective behavior system that I am studying has some sort of phase transition. But it is not so easy to detect, particularly in biological system, because of multiple reasons, and more particularly this in cellular system. The first reason is, most of the time you do not know what is the right control parameter. What will you control so that you see a phase transition? I'll give an example where the control is very easy to detect. For example, there are very interesting experiments where, see, you have, if you grow some embryon, particular type of embryonic stem cells, and as they increase their mass, after some time, because of interaction among them, obviously they are talking to each other, one set of cell will go into one differentiation path, the other will go another, and they will form a structure like ball-like structure, where the surface one has a different cell type, whereas the other cells are in the middle. Right? You can do that, people do that experiment in lab. Now, this phenomena that this structure, this differentiation and this structure will form can happen only if you have a particular seeding density. If your seeding density, that means the number of cells you are starting with, is less, then you will never get it. So in this type of experiment, the control parameter can be cell number that I am starting with. It's very easy to guess that it will be. But think about a process where there is a complicated biochemical processes going on which leads to some new property. Which one should be the control parameter? Which one you should vary? You do not know beforehand, right? You can keep trying, but there is hundreds of them. So to decide which is a control parameter is very tricky. Many a time it is very easy to get a feeling that there is a threshold behavior, but to pinpoint which behavior I will measure quantitatively so that I get this type of behavior, threshold is happening, is very difficult. So for long, it is not that the biologists are stupid, they do not understand these things. Many of them understand better than me and you, many of you. But the problem is in experimental biology, it is very difficult to get these things, measure these things. So nowadays, one important trend in this field is that rather than looking for all these control parameter, order parameter, can I get some proxies which are measurable, and that proxy will tell me that the system is undergoing phase transition, right? Some proxies, and rather most of the proxies are based upon this critical point, the threshold point, because the system shows certain particular type of behavior in these thresholds, right? So if I see that type of threshold behavior, I will say possibly it is going to a phase transition, even though I do not know who is the control parameter and who is the order parameter. I hope I can communicate, right? Okay, so now I will move into that questions that if I have to understand any collective behavior in terms of phase transition, and I have to know how things behave near the critical point, what type of techniques and tools I should use. Fine. Now before I jump into that, let me give this one. See, the whole thing is I am trying to impress you that, see, you possibly when you do experiments in a biological system, you have no handle to control a control parameter. Maybe possibly you even don't know who is the control parameter. Possibly you do not have a clear definition of order parameter, the parameter that will show change in drastic change. For example, for liquid to gas or solid to liquid transition, we know density is a very good order parameter. But suppose for a biological problem, you do not know any such parameter, right? And then you want to use the ideas of phase transition, you will create models, right? And you want to understand them in terms of phase transition and critical phenomena, but you do not know these controls and these variables details. What is the utility? Why we should do it, and will that work at all? See, this whole field, whether you call it a study of collective behavior or study of complexity, whatever, it relies on two basic beliefs, I will say, right? The first belief is that when we talk about laws and principles, they are not the way biologists talk about mechanism. When a biologists talk about usually mechanism, that is very specific for a particular phenomena they have observed. And for example, if you have done cell culture based experiment, the mechanism of a same phenomena in one cell line will be different into another cell line, right? That's not principle, that's not the law we are looking for. Whenever you try to get these laws, right, or principles behind some phenomena, it should have a larger applicability. It should be applicable. That's the basic beliefs in science, right? That's what we do science. So there must be universality in the diversity. So if I want to use the concept of phase transition, criticality to understand collective behavior, I should be able to apply those concepts not just in planar cell polarity the way I will show you, but in case of any other biological system, even non-biological system also. That's the thing. And when you do that, the second belief is very strong, is that when you see a very complex system with an emerging property, which sometimes you find difficult to even understand, right, and comprehend, that doesn't mean that the underlying rules and principle has to be complicated, right? So the whole idea is that the rules are always simple, the laws are always simple, but when we repeatedly apply that, eventually a very complicated behavior emerge. And in fact, Wolfram took it to extreme place where he says that every law of now, almost every law of physics are coming from their cellular automata rules, right? So the whole idea is there that you should have simple rules which are working below at the lower level, and you are seeing some higher level properties because of those rules, right? Now this is, you can always argue, do I know there is a theorem to prove that? No, this is belief. That's how you work on, right? So if you want to, build this, the question is, am I the only person I'm talking about it? Not really. There will be hundreds of papers and all these things. Right, I could have given you a long citation where everybody talks about that, rather than I just ask ChatGPT to concise that, and that's what it is saying, right? That whatever you see, there is a very complexity, mind-boggling complexity, but the underlying laws are simple, right? And just to remind you, many of the diagram, including the first diagram that you have seen, many of my diagram in the presentation will be actually AI generated. I haven't taken the trouble to do that. Just a disclaimer beforehand, so don't blame me later on. Fine. So if those two are the pillar of your beliefs, that you want to understand collective behavior or any other complex system in terms of those two beliefs, that it should be universal among the diverse system. At the same time, I will create a simplest or the smallest model possible. Then you cannot go into detail, every detail. You cannot. Because if you go into every detail, you will get lost. Fine? So you have to remove the clutter. What should you remove? That's the first question. The first question is what we should do, and that's what the general practice, and it is becoming predominant nowadays, is that, see, you look into the literature, talk to your collaborator, biologists and others, and try to find out what they call mechanistic information, mechanisms. This molecule activates this one, this gene expression changes, this gene expression happens because this transcription factor bind to this enhancer, all this information. And then get rid of those names and other things. Try to distill them into some logic. The way we make Boolean networks, we distill the whole thing into logic sets, right? So you build the logic. It does not matter how the logic is implemented. You get the logic and use those logic to create a very simplified model. And obviously, that will be a toy model. And the model that I will discuss tomorrow is also a toy model. Whenever you will create a toy model, it has some limitation. If it is a toy model, obviously you can easily modify and use it for a large number of different systems showing similar behavior. So it matches with your expectation. You have a small cis model, very few parameters, but at the same time, it can explain the behavior of a large disparate system. But it comes with a cost that it will be very bad to precisely predict the behavior of an individual system. It will be. Right? Now the question is, you have to take a call on this. What I see many a time is that many people who works on, many students, even faculty members who works on mathematical modeling biological problem, they actually make reduced model, right? Even if you are creating a mathematical model, suppose cells signaling for EMT, right? You are actually making a subnetwork model. You are not considering all the molecules. And when they face arguments, many times they backtrack and say that, no, yes, we understand it is more complicated than what I have done. I will say, insist, please don't do that. Your purpose is not to make a complicated model. Your purpose is to make a simplest model possible. Right? So there is nothing to be shy that I am making a toy model. I am making a model which will be applicable to multiple things. I have worked over the years on doing experiments, parallelly making model and fitting models to experimental data. Then you land up in models which are overfitted. I change a cell line. Not only I change a cell line, my students, two students, their handling of the same cell line is different. The data does not match with the model, right? Because it is overfitted model, right? So overfitted model may be sold as a very good mechanistic model, but actually very bad for science. So there is nothing to be apologetic that I am making a model which is very simple and cannot give me a precise prediction about how the cell will do. The question is, will it be useful for multiple cell types, starting from a human cell to a bacteria? If you can achieve that, that's what the goal. Fine. So what we expect from here, this type of model, and the model that I will discuss later on also, is that not to precisely predict what will happen, but rather give me a goal post. What is possible physically, what is impossible physically. But that's a very good thing, because if I can say, see, I am creating a planar cell polarity model which cannot tell you exactly what will happen in the Drosophila wing, but it can tell that, say, these things will not happen at all. So you will not design an experiment to check those things, right? So you are narrowing down. And also, in a way, it is getting predictive. See, for example, in classical physics, we say math driven because we make the mathematical hypothesis, mathematical model first and then go for experimental validation of that. This is similar to that. I am creating a toy model. That toy model make a large, tell me a window opportunity, and then an experimentalist try to look into that window, rather than doing n number of experiments just like Edison did to develop a light bulb. right? So that's what the toy model is all about, and we have to remember that. Now when I talk about toy model, the first thing obviously if you have studied physics will come, the question of Ising model, and which is related to phase transition. So as our discussion will, there are many toy models obviously. I will focus on the phase transition thing because that's what is related to our problem. So this is a classic example, second order or continuous phase transition for paramagnetic thing. If you are above the Curie temperature, the material has disorder, right? So magnetic dipoles are randomly distributed, so it does not have any innate magnetic moment. Whereas if you cross the Curie temperature, then as you reduce the temperature, slowly these moments get aligned with each other, and eventually you get a ferromagnet, right? That's all. Now you have to create a model for this, right? And if you have done any statistical physics course, you know the wide 100 years old toy model called Ising model. And remember, believe me, Ising model is really not a very good model. It's a very bad model if you want to match its prediction with a real magnet. No, not really. But the power of this 100 years old model is that it is so useful in so many diverse systems. I will give you an example which is very odd. Is that we usually say that most of the desk and computing time, most probably in the model which has consumed most of the desk and computing time in physics world is this Ising model. Because this has gave impetus to create hundreds of different types of spin model, to understand different type of physical system, biological system, evolution of, to understand evolution also. Not only that, this has been modified to understand economy, social behavior. One classic example is the voter behavior. Imagine that on a particular topic, you have two choices, right? Just like a spin can be up and down. Each of these magnetic particle is nothing but you, and surrounding is your friends and family. Each of them has an opinion. Their opinion affects you. So in this way, and there is a noise in the system, right? That's like temperature, work like temperature. Then how, as a whole, the opinion as a whole in the system evolved, the society evolved. So many types of this type of model has been created based upon Ising model by modifying Ising model. So that's where the power of a toy model is. You start with a very simple idea, very simple model. It captures large number of behavior, and I can apply in many other fields. So if I go into it, what is happening in Ising model? The simplest one, two-dimensional one. One dimension doesn't have much interesting thing. So in the two-dimensional one, each of these are, you can consider one particle or atom. Each of them has associated spins, right? Up and down, magnetic moment in that sense. So as we are at a particular temperature T, there is thermal fluctuation, and they're flipping, up, down, plus one, minus one, right? They're flipping. The idea is, if this one is here, it has four neighbors. These are not neighbors, right? These four neighbors. So this fellow want to align its moment with his neighbor. Fine? And they are all flipping. And there is flipping depending upon, obviously, on temperature. If you increase the temperature, there will be more noise, they will flip more. Now, to understand the equilibrium behavior of that, that's very important. We want to understand phase transition as an equilibrium process, right? So to understand the equilibrium behavior of that, we need a energy term for this whole system, not individual spin, the whole system. And the Hamiltonian in that case takes this form. I have truncated, there could be another term in your textbook because of the external field. I'm just removing that to make it simple. So Si and Sj, suppose this is ith one, this is the jth one. So Si and Sj are the spin, which you can move plus one and minus one, and J is the interaction term. So you sum over all the possible pairs, right? Now how do you get this one? Okay, there is details, exhaustive quantum mechanical calculation based upon the exchange interaction. You can go to this type of form, but I will not go into that. If you have studied statistical mechanics, possibly you have done that. But I will insist that don't go into that. Just look into the power of this formulation. Try to get the logic of it. Because if I can get the logic of it, then I can use it in so-called non-physical system also, where your quantum mechanics will not be applicable, right? So the whole idea is, two fellows are there, two entities are there, each entity has two property, binary, either upstate, downstate. Vote for Modi, don't vote for Modi, something like that, right? And my behavior depends upon my neighbor's behavior. right? And this interaction between me and my neighbor has some sort of energy, some sort. I don't know what type of energy. If you are talking of voters, then obviously the classical energy you learn in physics will not make sense. But you think about there is some sort of force, some sort of energy, potential is there, right? So there is an interaction energy between them. It's quite unphysical, right? But I want to capture that, so I can capture that in terms of J, right? So that is why I'm saying, look at the Hamiltonian, not is derived from a quantum mechanical calculation, but think that it is capturing the logic of the system, the rules, law, right? And then what you do, if you have the energy term, then you can obviously calculate the partition function. If you have the partition function, you can calculate all thermodynamic parameters. But usually, as you know, as the system, even for this system, that will be very difficult to do because the configuration space is very large. So what you do, and for mostly for non-physical system, also you do like numerical simulation. There are many algorithms. I will take this one because this is the easiest one to understand. So what you want to do is that you want to simulate this system in such a way, you start with a random configuration and you want to reach the equilibrium, right? So if you remember the definition of equilibrium, there are two criteria I have to fit. One is detail balance has to be valid. That means if I am in state I and state j, this is two configuration of this, so the rate of going from I to j and the rate of j to I are same, right? That has to be met because that's the definition of equilibrium apart from ergodicity. And then we know that at equilibrium, this is a closed system, so we should have the Boltzmann distribution should be applicable in equilibrium, right? So that will be a stationary distribution if you consider there's a Markov process. So what you do, you very simple to implement. Even I have tried with the class 11, 12 students writing it code in Python and doing it, right? Very easy to implement. So what you do, you calculate the energy of the system using the Hamiltonian that you have done, then randomly pick a spin, any of this fellow you pick up, you flip the spin, right? Plus to minus or minus to plus, and then recalculate the energy again, calculate the energy difference, and then you accept that flip using this rule, the minimum of 1 or e to the power minus del h by t. So if you are modeling using this approach to model a non-physical system, then you are in trouble. What is the definition of time, right? Sorry, temperature, right? There isn't, in terms of your modeling voting, what is the temperature? Okay, you do not have temperature, measurable temperature by thermometer, but don't we say that it is the contest is heating up? What do we mean? That means there is lots of noise, right? Lots of fighting going on. So you can use a parameter which is equivalent to temperature, which will add the noise in your system, right? More noise. So anyway, you can implement this one, and then you allow the system to equilibrate. Once you are happy that you have reached the equilibrium, that means your energy and magnetization, all these things will fluctuate around a mean. It will there be not much fluctuation. Then you collect the data at particular interval, average those data, and you get almost every thermodynamic parameter starting from magnetization, magnetic susceptibility, heat capacity or specific heat, everything you get, right? So I will not discuss detail of that. I will discuss something similar which shows similar this type of phase transition, but actually not so-called a thermodynamic one. But before I go into it, we have to remember, see this one, if I do the plot, in this case also if I do simulation at different temperature, that's why I have a critical temperature, Tc. So before Tc, I will have almost no magnetization in my experiments also, simulation also, and then it will be like this. So if I say this is the average magnetization, usually you take the mod of that, right? Because magnetization can be positive and negative, so you take the this one, right? Now, as I was saying that, see, in phase transition, I may not in real experiment, in biology particularly, I may not know who is this control parameter. In my simulation, it is very easy. I may not know exactly in a biological problem what is the order parameter here, right? So rather, we try to focus on some proxy, something which is characteristic of a phase transition, particularly suppose I imagine is a second order phase transition. That means one of them is what happens in this critical point, right? One important feature which is now usual, many people in single cell biology are using, is that as we approach from any direction, from this side or this side, actually the noise in the system increases. In fact, if you do numerical simulation in this and you plot the variance of m, right, So in this case, you will see it will be like this. This is the Tc, the time temperature in this direction. So that means as I approach the critical point, the noise in the system increases, and that will happen in your simulations also. So nowadays many people who are trying to understand phase transition in cellular system, and they have a huge RNA-seq data type thing, they try to see whether from that RNA-seq data they can measure some measurement of this variation, cell-to-cell variability. If they see that at different conditions, this variability all of a sudden is increasing, that means you say that you are approaching a critical point, right? And this has been used in, I think Sitobro also has worked on that in economic system, right? That it happens that right. Now why that happen? Another property is that in this case is actually what we call critical slowing down. If I move the system in this side, I'll slow down. When I coming back, I'll be very slow. Now, you can understand it from many perspectives, but I will use one idea which you will find very useful if you try to understand many biological problems. See there is a famous thing, if you have a physics background, you must be knowing, there is a Landau generalized model, like phenomenological model in terms of free energy. What they did essentially, if I don't go in details of that, they eventually created a free energy which is a function, which is a polynomial of the, what we say, the order parameter. For example, in this case, temperature. So how does that look like? So for a second order phase transition, the free energy, which depends upon, suppose order parameter in this case is m, magnetization, I have a constant term plus AT, I will say what is T, into m square plus A4, another constant, into m to the power 4. M's are the order parameter, right? This one. So now this is the free energy thing. T is nothing but a reduced form, you are unitless. So T minus Tc, how far you are from the critical temperature, divided by T, so that it scale it from 0 to 1, right? In this, around 0. Now, if you look into this plot diagram, what you will see, when you are in this region above Tc, right? In this case, your free energy landscape versus m, it should look like something like this. So you have only one minima possible. Fine? Fine? So whatever you do, the system will always come here. So that's why I have one. Fine? Now what happens in this case? When I am further away from Tc, right? So in that case, small t will be negative. In that case, you have the free energy landscapes looks like this. Fine? How? Because you simply put it, if you have a Desmos plotter in your hand right now in your phone, you can plot this function. This will be the behavior, right? It is a quadratic, to the power 4 term we have, so it will be like this. What happens in this case? I will draw it separately. In this case, when you are at Tc or very close to Tc, this one, which is a very narrow point, right, single minima, this becomes flatter. Fine? So think about it, you are a higher temperature, you have this shape of the energy landscape, you have only one possibility here. Whatever you do, you will go there. Then you move towards Tc, slowly the shape of the landscape becomes like this, where you have wider minima, right? Wider minima mean, remember this axis is order parameter, so I can be here, still I have the minimum energy, I can be here, still I am the minimum energy, I could be here, still I am in the minimum energy. So multiple values of m can realize that. And I have thermal fluctuation, so I'll move. So that means that's why I will have more noise in these. Not just in your simulation. We can say now that any system which undergoes this type of second order phase transition, if you measure, you have some measurement of order parameter, that should fluctuate near the critical point, right? So that is why rather than studying exhaustively, try to plot this type of behavior where I have order parameter versus control parameter, people nowadays to study whether we have a signature of this type of increase in noise or not, right? Now the another associated thing that you can understand from it, if you read any developmental biology book, paper or talk, obviously I'm sure you must have heard about what we call symmetry breaking. Yeah.
So you mentioned the graph at critical temperature, right? So the width of that thing is the characteristic of M, or it is?
No, it will be characteristic of your terms.
Oh.
Right.
Okay.
That we do not know what is the value. Fine. Remember, this is just a phenomenological model, nothing more than that. Fine. You have a question there? Is this drinking water? Yeah.
So you mentioned in that graph of M that the minima was widening. How exactly is that helping us?
Okay. So in this case, the minima is very narrow, right? One single point, one solution actually, right? So that means there is only one, theoretically only one possible value of M which gives the minimum. Here this is quite wider, so it's a wider range of values of M, right? Now any system has noise, so you are fluctuating, right? Or you can anyway say there may not be exactly same minima value, they are close to each other, very close, so it's very flat in that sense, right? And that is also the reason that if you disturb me from here to here, I really do not have a driving force to push me back to the real minima there. That's why it slows down also, right? Now one associated question, concept that I will better before I still move, I should inform you that, see, whenever you talk about developmental biology, any meeting, we heard of symmetry breaking, right? Symmetry breaking in a common sense from there is because once upon a time I was a ball of cells, identical cell. From that I have got this body, now I am very proud of it, right? So essentially I was symmetrical, isotropic. Anywhere you look at me, I am identical because same cells are there, but now obviously I am not. So this is in a way symmetry breaking. And this is similar to if you think about solid liquid phase transition. The liquid has isotropic property, translational invariance is there. I can go anywhere, I will find the similar other molecules around me, but if I take a solid, I have a particular lattice structure, I cannot just go in any direction to see the same units, right? So it is also symmetry breaking, and symmetry breaking is also in a way, you can think about ordered disorder. The liquid is disordered, whereas the solid is more ordered, right? Now, the symmetry breaking get much more interest, much more solid if you think about this one. See what will happen. See, usually all textbook and classroom, we only show this is 0, this is 1. But that's actually not true. If you do experiment, this is my magnet ferromagnetic material, if I go below Tc, I am not sure whether this side will be North Pole or South Pole. This is completely random, right? So that's what is happening here. See, I am symmetric here because I have only one option possible. As I jump to Tc, I have two options, +1, -1. But obviously I can stay in one position, right? I cannot be in two positions, right? So either I will go in this or in this. So obviously symmetry is broken in that sense also, right? And how I go it decided because of the thermal noise, the what we say, the noise in the system, which is essentially making it a stochastic process. You cannot beforehand say whether it will become +1 or it will become -1 in that sense, fine? So these are the key concepts. Rather than going to details mathematically, I just wanted to highlight because these themes comes regularly in developmental biology, phase transition, any sort of phase transition, right? Particularly second order, where I will have noise at the critical point, and it is essentially a symmetry breaking problem. Now what I will discuss more, because this will be useful for us, this is the athermal system. Athermal system means, there is no issue of temperature, no issue of heat, right, nothing. This is a geometric problem, right? And again, you may have studied it. This is called geometric phase transition, and it has a good name called percolation. So what we have, I have a square grid, fine? It can be of any shape. Square is the first one people thought, easy to do. So I have square grid, there's a whole white color. What I do now, I color some of those grid boxes black with a probability P. P will vary from 0 to 1 as usual. So if I do that, what happens? You can do a simple computer experiment. This is one realization, right? Every time you will not get the same pattern because it's a probabilistic thing. So one realization I get like this, probability, that means one box can get a color black with a probability 0.1, I get this type of picture, and as I increase the probability, more and more boxes get filled. So what you ask in this case is that, remember, tell me the probability P at which I get a continuous path of black cells, black boxes from lower to higher, right? So in this case, I do not have a constant path, right? I do not have path. This path I do not have actually any path to go on that side. Here also it got broken because these two are not neighbor. Remember, they are diagonally, right? Here I have a continuous path. I can go from here to here. Fine. So when I get this path, I call the system as percolated. Because this model, this system has been, this toy model has been used extensively for two cases, for diffusion of liquid through porous media, right? And also semiconductor things. So you can imagine there are holes and other things where through the electron can move, jump, right? So how many of them should be there, right? So the percolation means you started something on this side, it percolate the boundary on the other side. Fine. So this is a percolation. Now if I get the probability, you can do a simple simulation to get the probability. So it is a probability of site occupancy, the P, and you do lots of the repetition of that, make an average of that, right? So the percolation probability, the chance that the system will percolate, that means I will get a path from this side to this side. The probability of that, if you plot, you can see the behavior is like this. Up to this, I think it is 5.29 or something like that. Then all of it is 0, and then all of a sudden it increases and reaches 1 very fast, right? So it is typical like a second order phase transition you can see. Just now in case of magnetism I showed, right? I have a critical threshold beyond which the order parameter changes very fast and saturates. Now this one is actually not very useful. This order parameter is actually not very useful if you keep on changing the lattice system, what type of lattice you are working on. So a much better estimate what we call is percolation strength. What you do, you try to find out this percolating cluster. Means these two black, if they are neighbors, they make a cluster of 2. If there are 4 of them, I have a cluster of 4 black thing, right? So you try to calculate the size of the cluster which is percolated, meaning it started from this side and it has gone to the other side, right? And you plot that and you divide it by the total number of boxes, right? The grid size, L into L square. So that is called percolation strength. And that also show this type of second order phase transition, where up to this point, the critical point of peak, we call PC, it remains almost 0, and then it increases sharply, right? Now, still these.
Excuse me, sir. 2 quick questions. First question is, those plots, those squares, are they for one simulation step?
Okay. So you do not need multiple step in this case.
Okay, and so that is for one
single you can do, right? What you can do, you make a L square array and you choose the value 1, 0 in each of the cell based upon a probable quantity.
Okay, that's fine. So could you explain what percolation strength is again?
Yeah. So what you are doing in this case is that you are finding the cluster. Cluster means this cluster is made up of multiple black boxes who are neighbor to each other, right? So you find the cluster which is percolating. That means we start from this end, goes to the other end. So for example, this big cluster, this whole thing is actually one cluster and it has percolated. So you calculate the size of that. And you iterate this whole thing, you get the average size of that, and you divide by total number of boxes. So that's why it got scaled from 0 to 1. So that is percolation strength, right? It is much easier to calculate, and also you have much more better mathematics because you can consider this grid is actually infinitely large. So the percolation happen from an infinite system, and lots of our calculation get easier, derivations get easier. Now the problem is this idea that the cluster will start here and touch the other side is not applicable for many systems. For example, suppose imagine I have a network, right? Network means something like this. I have nodes and I randomly join them with two nodes with a probability p. So I am evolving a graph, right? So in this case, it is also like you can consider this a percolation problem, and then also you have cluster. Cluster means nodes connected with edges. So then what is percolating cluster? There is no direction in this case, right? So nowadays, actually what we do not consider like there is something to percolate from one side to another. In general, what you do in general percolation theory is that you define percolation strength as the size of the largest cluster, relative size of the largest cluster in the system, right? If you are simulating in a finite system, obviously that will be finite. If you are doing it in infinite system, obviously that will be infinity. Rest of the thing will be finite, fine. Is that clear? Okay. So then, you can actually have many different types of, this is called simple 2D random percolation. And one point I don't know whether you have noted or not, this we will use for collective behavior studies, but right now there is no explicit collective behavior, right? There is collective behavior, but no explicit local interaction. Because in case of your icing model, each particle or each atom has neighbor interaction. Here is no interaction. It is only thing is there is a stochastic process, and this stochastic process itself is driving this organization, nothing more than that, right? This is quite important to differentiate between these, right? The other example. Now, as I said that we are most of the time interested to not on how this whole thing behave, because in many real system you will never capture the whole thing. That is the problem. But rather, if I have a belief that the system undergoes some sort of percolation transition or any second order phase transition, I should study its behavior near the critical point. And one important issue here is that the issue of critical exponent. What is that? Okay, so let us take a very simple example. I think there is a mistake here. This t will not be there, right? Fine, this t will not be there, fine. This equation I have just written here. So now, if you consider that this t is, we are at near the critical point, right? If we are at the critical point, this t will be 0, fine. And if I am near critical point, it is non-zero but smaller, fine. Now at this critical point, if you find all the solutions, mean you actually differentiate these with respect to, or with respect to t phi here. So you get multiple solutions, and the equilibrium solutions will take the form of t to the power half. You can easily see here, right? Because you will, if you differentiate with respect to phi, I will get here phi, and it given phi to the power 3. So you take out the phi out, that is one, and set the other side 0. So one solution is obviously t to the power half, right? So now I can see that means near the critical point, what is happening, this order parameter phi, what I wrote as m in this case, is actually scaling with t to the power half, fine, isn't it? So that means this is a sort of power law, that the phi, the thing is scaling with the control parameter with a power. Now, if you get this intuition, then there is a whole theory, where people have derived different sort of power law relation between different measurable thing at the critical point, near the critical point, fine. So like how? So the general idea is something like that, that if x is a thermodynamic parameter that you are measuring, which can be magnetization, this could be percolation strength, this could be magnetic susceptibility, or suppose specific heat, or in our case I will show one which called average cluster size in percolation, some property you are measuring, that should scale with your order parameter, which is reduced order parameter, because you are scaling it with a power omega, right? And you should have a constant here. So for example, if you remember this diagram, so variance sum m is x in this case. I can rescale this t as small t T minus Tc by Tc, right? So then here you can easily see there is some sort of power law relation, and it is valid on both sides of the critical point, right? So that's why the absolute T is taken. A is a constant. A can actually vary. For example, in this case, A on this side, A on this side, the constant term can vary. In this example, A here is actually 0. On this side, I have a value of A. That's why I have this type of behavior, a quadratic thing, right? Root over of T is coming. So this is, there are derivations to get this type of thing for many well-known model, but for rest of the cases is actually assumptions or believe that they will be valid, and we try to fit to data, and thankfully the data matches with this. So the whole idea is that it does not matter what type of systems you are dealing with, right? It does not matter whether you are working on an Ising model or a 2D percolation. It does not matter exactly what is happening at microscopic level. The whole philosophy or belief in this case is that this omega, these critical exponents, are independent of the microscopic details, microscopic mechanism at the lower level, right? What it depends upon? Usually it depends upon the dimension of the system. You cannot compare the critical exponent you have studied in an Ising model in 2 dimension and Ising model in 3 dimension. They will not match, right? But otherwise, it does not depend upon how you have defined interactions, right? It does not depend upon how you have defined exactly the Hamiltonian energy function. Eventually, this omega will remain same. Will it remain same for all system which is undergoing this type of second order phase transition? No. For certain second order phase transition, this omega will be different. But what we can do, we can group different phase transition problems in certain categories. Category A, category B, category C type. So all phase transition problems or models which falls in category A, these critical exponent for all those systems will be same, right? So this is the whole idea of universality. You, from a diverse problem, you are making them narrow, you are putting them categorizing. For example, liquids, in some cases of liquid gas critical tricritical point is if you do the experiments, people have done the experiment and calculated the critical exponents like this, they matches with the critical exponent of 2D Ising model. So that means that model, that real thing actually belongs to the universality group or universality class of Ising model. So that makes us, if you remember what I started with, that we have a philosophy that we want to make some universal idea for disparate system, lots of different systems, right? So that's why when you are starting a phase transition problem, it becomes very important for us to calculate these critical exponents from data and try to see whether that belong to a known group or not. It may not, right? In that case, you have discovered a new phase transition problem, but otherwise in most cases it falls into a particular group which is already known. Now, let us look into some critical exponent which will be useful for us in the next talk. Is that in case of percolation, we define percolation strength like this. CL is the largest cluster divided by, I am talking about 2D system, so L square is the total number of boxes, right? In that case, remember in case of temperature based system, temperature was my control parameter. In this case, my control parameter is probability. So the reduced control parameter is P minus PC. PC is the critical probability, right, where the transition happens. So the percolation strength scales with that reduced P as this power law, where critical exponent is beta. Average cluster size, which is you can easily calculate, that also has some exponents. Correlation length, which is the characteristic of the cluster sizes, right, also have some scaling. And cluster number density, right. So what is the probability density of the clusters of different sizes, mean number, right. So that also scale with its number to the power minus tau. Now for 2D random percolation, all these thing has been exhaustively calculated, fine. For example, these are the values which has been calculated. Now remember, these values are true for 2D random percolation irrespective of the finer details of your model. Let me give an example how I can change the final detail. I can create two very simple random percolation models. One random percolation model is fine. I will fill them with color the way we have done right now. So I have filled this one, this one, this one. So this is a cluster. Fine. Another random percolation model could be something similar. This will be called site percolation. Fine. So rather than filling them, I can say I will add edges randomly. It will call bond percolation. So the rules, the microscopic rule is different, right? But their behavior, critical exponent will be same. Now let us look into something else. I can have, still now what I was showing you a square lattice, right? I can have triangular lattice also. In square lattice, every member has 4 neighbors. Whereas in triangular lattice, each member will have 6 neighbors. Fine. So will the critical exponent be same in that case also? Yes, the critical exponent will be same, although the lattice structure is different. So the microscopic detail is different, but their critical exponent is same. So they will be in the same universality class of 2D random percolation. But one thing will change. See, the probability at which this critical transition is happening, that is not a critical exponent, right? That will depend upon your lattice system. So for example, in case of 2D square lattice, this is 0.593, whereas in case of 2D triangular lattice, it will be 0.5. That is quite reasonable, because if I use this random percolation type model to model something else, where suppose the P is not probability, suppose that is the price of shares. So obviously, share prices is not comparable with probability, so these numerical values cannot be same. But if that model also falls into 2D random percolation model, the critical exponent that we have discussed till now, like this, these parameter values will be same, but this will not be. Fine. So the whole idea is that, okay, I have few more minutes. I will not go into this. I think this one will be much interesting. So the issue is why I am doing all this. Obvious reason is tomorrow I have a talk where I will use this phase transition, icing model, percolation, all these things to understand a very simple toy model which has been inspired by the planar cell polarity in Drosophila wings, right? So to understand that, I thought it will be better if I go through this basic thing, because these tools we will be using, right? And all these words will come, phrases will come. But the question is there in real evidences that percolation or this type of phase transition happens in biology? There are many. I have picked up 2 examples which matches with percolation behavior. Again, remember, in this type of problem, as I am hammering repeatedly, that it is very difficult to measure or identify who will be the order parameter. So most of the time we try to look into the signatures of phase transition, like critical behavior, power law behavior, which will happen in the critical point, right? This example, in this case you have egg follicle epithelial cells. So where what they have done, they have stained the actin filament possibly, right? So they all get aligned in one direction, like a compass needle, right? Now, how they do that? The question is, obviously there is cell-to-cell interaction. At the same time, people also believe there is a global signal, because that's how they can detect that side up or that side down, something like that. Now, some postulates were there that the fat is involved in that, so they created mutant. If you create a mutant, actually this whole thing gets jeopardized, you get disturbed. The question is whether it is fat in this case is involved in cell-cell interaction or something else. What they did is I have not shown here, very beautiful experiment that many developmental biologists do, what we call mosaic experiments, right? You have a base of wild type cell in which there are patches of mutated cell, like a mosaic, and you will now see different type of behavior, very difficult to do, as I understand. So they have different mosaic experiments where they have mixed wild type and mutant fractions. Fine. So you can see when mutant fraction is less, almost all the cells has this type of alignment, including the mutated cells, right? Whereas after a threshold, both the mutant as well and wild type, they fail, right? So that means this is some sort of phase transition. From this side, you can draw a line, fine? Now, is it percolation transition? Okay, what they have done several experiments, and from that they have identified that no, fat is actually not disturbing cell-cell communication. That is not happening, right? If fat is disturbing the cell-cell communication, then possibly in that case, some of the fat cells would not have got aligned, right? Those mutated cells also. Based upon those experiments and these observations, they created a percolation model. What is the model? You think of an array of cells, hexagon if you imagine, right? And some of them are wild type, some of them are mutated. A global signal is coming from this lower side, suppose, and it goes along the whole system from one cell to another. That means each cell is working like a, in a relay race we transfer the baton like that, working as a relay. Now when you mutate these cells for fat, these cells fail to relay it, fine? So the question is, if the whole system has to percolate, if the whole system has to align in all direction, then there must be sufficient continuous path of this relay of information. If you do not have this continuous path, then the system-wide alignment will not happen. So then this is equivalent to a percolation problem. What fraction of mutated cells should be there so that I get a continuous path, at least one continuous path of information transfer. So across the whole length, information is getting transferred from the lower to the upper side, and then there is cell-to-cell interaction, so that information is getting shared. So you need at least that much of wild type cell so that I get a continuous path from this side to that side for information transfer. And if you create a model of that, and they created that model, and then this type of behavior you can see. Obviously in that case model there is much smoother, not like this. So the whole issue is you cannot use lots of mutated cell. You can use mutated cell up to certain fraction, that is the below PC critical point. After that there is no continuous path of information transfer, right? So if there is no continuous path of global information transfer, then these cells, even they are wild type, they cannot align, fine? In this case, this fat gene is mutated. This D is, what do we call it? I forgot. D is aspartate. Aspartic acid? Aspartic acid, right? So that is mutated, fine? FAT, fat. It is a cadherin, as if I remember correctly. Okay, so this one is another example, very interesting one. In this case, it matches with exactly what I was trying to say, that you will not have complete. In the previous case, at least you have some sort of phase transition diagram, right? Because if you remember, yeah. Sorry, they are actually checking.
Did they actually manage to check it was in the percolation universality class?
No, they never checked the universality class.
They just made a model of percolation and checked.
And they were more busy actually to fit it to the original data.
Yeah. But I mean, many things would fit that, right?
Huh?
But many things will fit this.
Yeah, many things will fit this. As long as you can match this thing, that whether local information transfer is not disturbed, right? If you can make alternate model, obviously that will. Okay, this one is on subtilis. What they have? So this is a biofilm of subtilis, right? Bacillus subtilis. So these fellows, say when they have nutritional starvation, particularly if I remember correctly, in this was the glutamate starvation, right? Then what happens? They open up some ion channels, and potassium is efflux of those cells, and as the concentration of potassium increases around them, obviously the neighboring bacteria also get affected, and the neighboring bacteria stops uptaking the glutamate. So I do not have glutamate, I release potassium, you are standing beside me, you have now depolarization. You cannot uptake glutamate although you have a bag full of glutamate with you. So you starve. When you starve, you start releasing calcium again. So there is a wave of propagation of depolarization, right? And you have standard dyes to measure this depolarization. So you can make beautiful images. So you can see here on this side actually they have started the starvation, right? And they're measuring how, there are time dependent data also. I'm just taking one snapshot. This lighter color thing are the fluorescence thing where depolarization has happened. So you can imagine this whole biofilm as a lattice of bacterial cells, right? And in between some of them will lit up, that means they have got depolarized. So I can vary various factors. For example, you know, what was the initial amount of glutamate available and all this thing, and then I can see, do I see a continuous patch of depolarized cell from one end to the other, right? Now, as I said, in this particular type of experiment, they do not have any clue what should be the control parameter, concentration of glutamate at the very beginning or not, they do not have, right? So rather than drawing this type of diagram where you have a control parameter here versus you see some transition, right? What they did, they tried to see the behavior of clusters, fine? So if you remember, few slides back I have shown that cluster number density means this is the, you can imagine in a way is the probability of NS is the probability of getting cluster of size S, right, or frequency of that. So that scales using power law with the size itself, fine. So this is a unique property of second order phase transition where the clusters are formed and different type of universal class has a different tau value. So they try to measure that, because as I said, when you cannot find exact thing, you try to look at the different properties that critical their exponent. So here what they have done, they can easily do image analysis, find the cluster size and get the probability, and if you fit them, it fits almost 2, right? So the theoretical value in case of 2D random percolation is, I think, it will be around 2.0 something, fine? So from that we can get a guess that possibly this system also has percolation and possibly this is similar to 2D random percolation, fine? So I think I'm at the end. I have skipped one part. If required, I can discuss that separately. So what I try to impress you, I just broadly few topics. What is collective behavior and how phase transition is connected to that. The poster boys of phase transition model are Ising model and 2D percolation model. I'll use them extensively in the tomorrow's talk. And then I discuss about scaling rules and the universality classes, that there are some critical exponent which are characteristic features near the phase transition. So even if you cannot capture the whole phase transition process, if you can capture those critical exponent, you can say a lot about the phase transition happening, and that's why they are much useful for, you know, real life system like a biological system, like cell based system. Thanks a lot for your attention. Hope I have not bored you much.
Thanks, Biplab. Questions? I was like equally surprised.
In the experiment with actin filaments, where they showed the mutant fraction controls the, here they could check the neighborhood and
They could check the neighborhood, yes.
the correlate. So here I'm assuming it's randomly, they're randomly placed, right?
Yeah.
The mutants and the
Yeah,
wild
yeah,
type.
they don't have control. Yeah,
But if you control that, you should be able to verify.
possibly. I
But
don't know. I have no idea about this experimental system. Yeah, if I
Right.
understand how they do, I mean, I never seen people doing it. What I can, by reading those papers, what I gather is they have many type of things, like, you know, some of them are completely uncontrolled. Some of them possibly are using localized heat or something like that.
But correlation should affect in print.
Yeah, correlation you can. I think this paper was not very exhaustive in numerical calculations, but even if you have a random uncontrolled distribution, then also you can find the correlation. You can find distance by correlation also. From image you can easily do that. I wonder why they haven't done it, right? But you do not need to, if you think about correlation, because see in critical transition we see long range correlation. If I am in, I'm at the phase transition point, and after that actually what I am doing, you also get affected, right? Although you are far away from me, you are not neighbor. So this type of data can be calculated easily from this type of image data. Fine. So I don't know why they didn't did it, but one can.
Is there any natural, can you think of a natural biological process where this could be exploited, something like this?
This is a natural biological process.
No, as in this is a lab setup where you have a mutant and
okay.
I'm talking about compositions.
No, actually
like this,
the issue is, for example, see, you should ask the different questions. The question is why there should be a critical phenomena. Why?
You naturally wouldn't see
natural system. In a biological system, why the hell I need a critical phenomena? I mean, there is a threshold after that, right? So, in tomorrow's lecture, I will try to address that question. Why we need actually a phase transition type thing? Why? We can have a smooth increase, which is not a threshold behavior. I can have a sigmoid curve, right, without this absurd thing. That also can serve my purpose, right? So, I will not go into that. Usually, in other example, where you have a thresholding, in particularly in molecular communication, molecular pathway, these type of thresholds are very useful, because if you think about there, and that's the similar logic we will use when I will argue tomorrow also. The issue is of noise, right? Whatever you do, there is a fluctuations, and your system of information transfer can read that in fluctuation as the information itself and do something. So you make a cutoff. After above it, I will consider as a real signal, right? So many things, this whole issue of that Hill function we use to model transcriptional control, where we have this very sharp cooperativity and all these things, right? So the whole idea is there, that because the transcription factors are always there, and if you imagine a very simplified model where they are always hitting my location, right, where promoter region, then there will be aberrant transcription. You want a considerable critical mass of transcriptional complex to form, and then it start, right? So that type of similar logic should work here. In different cases, in some cases, particularly in case of crosstalk between neurons, right, where one neuron activating the other one, in that case the whole idea is, because that will be a completely different discussion, where they call it, they have self-organized criticality. In that case, they have tried to experimentally prove, and was quite a famous paper, although now it is quite disputed, is that actually the system stays near the critical point. It is not away from critical point.
Yeah, that's sort of my question. Like, criticality might imply power laws and these sort of relations, but the other way around need not be true, right?
I'm not getting. What is the other way around?
As in, if you see a power law, that necessarily doesn't imply criticality.
No. If you can have some other system which can have power law, you can have. I mean, this is not one in this.
So
if this is true, that doesn't mean that is true. No, that is not.
Okay. Thanks.
Any other questions? Chishman? Yeah.
Yeah, I mean, maybe I'll just follow up on what Harish was saying. I think it's an interesting line of discussion, because the question is if, I mean, we've worked so hard to figure out critical exponents, but the universality really only applies near critical points, right? Those relations of power laws only true near critical points. As long as you go away, as soon as you go away from the critical point, you're going to get non-universal corrections. I mean, some universal corrections, but also some non-universal corrections. And so the question is, do we have enough examples of biological systems that actually operate near critical points? And if they operate away from critical points, then is that universal prediction useful?
No, we do not have. The issue is, if you think about it, see, I'll give, in fact, this becomes very difficult. For example, when I started working on planar cell polarity, when you new topic, you got attention, right? You start reading. The first thing you pick up a review article, good review article from a good review, right? you pick up almost any review article, they will compare it as a phase transition, right? They will compare with magnets, very common, right? These metaphors are extensively used. So that means this metaphor, the stalwart in this field are using from the very beginning, isn't it? So immediately it will come to our mind, have they ever tried to do a similar experimental thing which will gather those information, right? Is there a criticality in really, right? Either I understand, because I will not blame people, because I do not have never done experiment on those type of system. I believe they are much more complicated than what I have handled ever. So because of experimental limitation, or because of some interest issues, what you are more interested in, you are interested more in molecular mechanism to know how the molecules, a particular molecule. There is a huge lack of information that to check those things, right? The same thing happens. It is very easy for me to give lecture without giving example that this happened. You have to dig very hard in literature to find out where people have done experiment to match this type of thing. Most of the time we are talking almost like metaphor, right? But slowly I believe that the type of different experiments are coming where you can have less intervention, more control, right? Slowly, possibly these alternate things will get. For example, this RNA-seq thing, to check out whether there is actually noise near criticality, all this thing in a biological system. Means many of our colleagues in India also do that type of experiment now to find out the critical transition, phase transition during EMT, where they do that type of studies, right? Single cell RNA-seq data, and to see whether the noise is increasing or not. But otherwise there is a dearth of data.
So if I may make just a point to that, like most of this neat theory of universality is to do with equilibrium phenomena.
Yeah.
Biological processes are inherently non-equilibrium, and in non-equilibrium, okay, so there's this directed percolation class, but we know that many non-equilibrium processes show exponents which do not fall in the DP class, and we as yet I don't think we have a classification of all the possible classes there are in non-equilibrium processes. So that makes this job even more difficult, I think. Okay, any questions? Okay, if not, let's thank Biplav once more. And so we break for coffee, and we'll be back here at 4 for the last talk of the day, which is going to be an online talk.